I wanted to talk about another type of application for the normal distribution. And if we back up a little bit and um, before we started to talk about the normal distribution, we talked about discrete random variables. And the random variable is basically a function where we input values from our sample space, and then our outputs are probabilities. So it's a function. It's a probability density function, it's called, and it is a way for us to find probabilities. And the one of the things that we ran into was that it's kind of hard if you take and want to have a bunch of different discrete distributions and then go out and collect data and then try to match up your data uh, or an approximation to whatever you've collected to one of those standardized types of discrete distributions, like the binomial. And there was a Poisson and hypergeometric, and there's lots of different types of discrete models out there that you could use, and it would be okay. And but another thing that works pretty well, though, is to use a continuous distribution to approximate the discrete distribution. And that's kind of what we like to do in statistics. And we find out that the normal distribution, which is continuous, is a pretty good approximator in a lot of situations. And that's what these examples are about. It's taking a discrete distribution, a binomial, and coming up with probabilities for that binomial situation by using the normal distribution. So again, our goal here is to show that the normal probability distribution has lots and lots of applications. So we like using it. It's pretty straightforward. We've been learning how to find area under the curve so we can come up with the probabilities. And so it is a very important part of what we're doing now in statistics. So this again, normal approximation to a binomial, and uh, if we go down, and he kind of reviews the binomial, and he said, remember that in a discrete distribution or model, we have some kind of finite number of possibilities, and in this case, he's saying we have a fixed number of trials, and we have a specific number of successes in n trials. P is the probability of success on any given single trial. And the probability of failure is 1 minus P. We call it Q. But basically, that's saying in a binomial distribution, that means you have two things that could occur. Okay, so our sample space only has two things that could occur on any given single trial, and then we're going to run multiple trials and then see what happens overall. And this rationale for using the normal is that if you look at a lot of empirical studies that were done, you find out that the results typically end up being normal, not always. Again, the normal can't be used all the time. But for binomial, when P and Q are not too far away from 50-50, it works pretty well. And one thing we want to do, remember that we're going to need here, and this is the requirements, that n times P greater than or equal to 5, n times Q greater than equal to 5. So that's what I was just referring to, that if we're not too far away from 50-50, if we're not like, 0.99, 0.01 on P and Q, which would give it a fairly skewed distribution, we can use other distributions when that occurs. But normal is a good approximator. So for the normal approximation, remember that the binomial, the mean, is n times P. Standard deviation is square root of n times P times Q. So Again, we had talked about that in the last unit. And there is something called correction for continuity that we need, because if we're working with small numbers, it will make a difference. And they say that basically this plus or minus 0.5, depending on what we're trying to find. So we're going to go ahead and run through an example. We're going to follow all these rules here, and I'll come back and talk about them. And we'll check this stuff first, and so on. And I'm going to use a different example. You can look at the example that he has in the book, and I'm going to come up with another couple examples for you that are not in this particular text. Right? So when we talked about the binomial distribution, we talked about discrete distributions. Again, you can use what we call the binomial probability formula. And if you remember what that was, is we had to plug values into this formula, or we could come over to the calculator and use it. And now what we're trying to do is eliminate using that formula, because the problems can become very lengthy with the formula. And it's a lot easier to use the normal distribution. And let's look at an example. Let's say that we have a situation here that we have a company that manufactures cookies. They manufacture and ship chocolate chip cookies. And we know that if there's broken cookies in the bag, the consumers are not happy. Okay. Now, let's say that through data collection, that we find out that in a bag of 24, so n equal 24, that we have um, 3 or more broken cookies, people get upset. Okay, so we want to find the probability then of 3 or more broken cookies. Okay. Now we need to know, and again, P is the probability of 3 or more broken cookies in that bag of 24 cookies, right? So we need to know then what's the probability that any single cookie is going to be broken, just in general. We're going to set that P equal to 0.05. Okay. So this is again the probability. We have n equal 24, p equal 0.05. Now, when we use the normal distribution, and we're going to come over here and do that, right? I got the normal curve here we're going to use. When we use the normal, we want to find area under that to find the probability, because right here, again, we want to find a probability of this. We don't want to use the binomial probability formula, because in essence, what happens is that to find 3 or more, that means you have to find the probability of 3 plus the probability of 4 plus the probability of 5, and so on and so on and so on. The whole way up to 24. That's one possibility for doing that problem. And that's a lot of work. We could do that much faster, but we need a mean and standard deviation. And we just looked in the book, and it said that the mean, since this is a binomial distribution, meaning that either the cookie's broken or not. Okay, so that's the only one of two things that could occur. Either the cookie's broken or it's not broken. So this is clearly binomial, 24 trials. Here's our probability of success, or in this case, a broken cookie on any given single trial. So the mean is equal to n times p. So the mean is equal to n is 24, p is 0.05. And if we, again, remember, we're, you can take 24 times 0.05, 24 times 0.05, we get 1.2, okay? So our mean is 1.2. Okay, so 1.2 is in the middle, right? Now, we're trying to find the probability of 3 or more. I'm going to draw 3 here, or more means out that way to the right. So we think of this as a number line. And then to find area under the curve, we need to use normal, CDF, and so on. But I've got my mean, but I don't have my standard deviation yet. So let's go here and we put a standard deviation, square root, n times p times q, which is equal to square root 24 times 0.05 times 0.95. Okay, so where did I get the 0.95? Remember that if p is 0.05, q is 1 minus 0.05 or 0.95. Okay, p and q are complements, so they have to add up to 1. So that's why we do the 1 minus the 1 value to get the other one. So these two add up to 100%. And then we got to go in to the calculator. Again, I'm going to clear that out and do second square root 24 times 0.05 times 0.95. So I get, we'll round this to 1.07. Okay. So we're going to round this to 1.07. There's our mean and standard deviation. So really that's kind of like, we didn't even really start the problem yet in a sense because we had to do a little bit of groundwork before. In most of the problems in these textbooks, they typically give you the mean and standard deviation, but they're just trying to emphasize the fact that, this was a discrete distribution, it was binomial, and they wanted you to run through and see this is not go out and collecting a sample of data. This is more of a theoretical idea of what happens in a binomial distribution over multiple trials. We're trying to see how we can use the normal to approximate that. So again, normal, CDF, and now here's the tricky part. This, you got to do the mean standard deviation, but we talked about you have to do correction for continuity. So you got to go half a unit below. And it may not make sense to you right now, but let's go ahead and run through this and I'll explain a little bit more in a minute. But half a unit, 0.5 from 3, so I'm at 2.5 in reality. Okay. So I'm really finding the area from 2.5 and greater. So I got to go 2.5, E99. The mean is, there's the mean we needed over here. And then now we need the standard deviation of 1.07. Okay. So we're going to plug those values into the calculator. And let's go ahead and do that. So we're going to clear this out. Second function distribution, normal CDF, the lower 2.5 to, okay, E99, got that in there. The mean is 1.2, standard deviation 1.07. Okay, so there's my shaded region, mean and standard deviations. Enter. Everybody should be there. And enter. So we come up with 0.11219, right? So we'll just round that to 0.11. That'll be close enough. Okay. So this area up here is 0.11, okay, or 11%. So probability of 3 more broken cookies in those bags of 24, meaning that, if you go to the store, and if this data were true, if you go to the store and you'd randomly kind of pick up one of those bags of cookies, there's about 11% chance that there would be 3 or more broken cookies in that bag. Okay, so that is, again, it seems like a lot of work, and it is for one problem. And this is a good example for the normal, how we use it. Now, are we going to have to do all of this work all the time when we do these problems from here on out? No. No, we're going to get past this again. This is just to emphasize in this particular section. So don't think that, this correction for continuity is always going to be there. It's not. That you're going to always have to, do the mean and standard deviation. And again, it'll be given. It's just in particular when we show this approximation, it's nice to see all the groundwork and how we do that. And it actually did save a lot of work from having to look at all those individually. And, we see the or in here. Remember, from probability, we said or meant the addition rule. So we got a bunch of things, or we could have used the complement actually to make it a little bit easier. But once you catch on to this, it's fairly straightforward. So we're gonna again, I'm going to just do this as a short video, and then because I have one more that I want to do in another separate short video, and finish up the unit dealing with confidence intervals. So we're going to stop the video right here, and I'll give you a chance to work on some of those problems.